Thank you very much. So I'm going to talk about TPMs and especially TPMs on embedded devices, which is something I see rather often in my line of work. So what I do is, as I've already been introduced, I'm pen tester, auditor, security consultant, whatever you want to call it. And we do, in our company, do a lot of that. And we also do a lot of embedded Linux devices. So basically everything around Linux, and a lot of it is embedded Linux. And we sometimes, and lately increasingly more, get approached by customers who come for various reasons to us, and some of them talk to us about TPMs because they have embedded devices, and with regulations like Cyber Resilience Act, NIS2 or something like that, they are now thankfully forced to take security more seriously. And they have, various goals like getting secure storage in place and working. And then they often come to us with, but we have a TPM that will solve everything, right? We already have it on the device, we just have to enable it. And the answer we usually give is, it depends. And you have to take care of a lot of things. And that's the goal of this talk, to give you an overview of what things can go wrong, what have gone wrong, and what one can do about that. So it's intended to be a guide for if you do that, so if you have an embedded device and want to use a TPM, but also if you're pen testing one. So if a device of that kind in front of you and it uses a TPM, maybe you can find some pointers here, which will give you a hint on where to look. Okay, let's start. What is a TPM? I assume most of you know or have heard of it. Just to briefly recap, a TPM is either a dedicated chip on your device, on your mainboard, or it can also be implemented in software. Then it's often called an FTPM, so firmware TPM. But it's just one kind of software TPM. There are more. There's an open specification by the Trusted Computing Group. We are now at version 2.0 of the TPM spec, and basically a modern Intel-based or AMD-based laptop, especially if you're running Windows, you have one in there, and it is used by Windows, for example. But also Linux uses it. It has a bunch of buses or a bunch of connections, which it usually uses. LPC is the regular one for Windows PCs or standard Intel PCs, but there's also SPI, I2C, which is more often used on embedded devices. They're rather seldom on embedded devices. It's not that common to use them in an embedded device because embedded devices, especially IoT, you want to produce them very cheap, and that's where the price of every little chip matters, and so they often skip away and do not add a TPM chip or something like that. But often also the system on chips also have some type of features that TPM offers already in the chip itself. So the vendor offers a vendor-based solution. But let's talk about the core features of TPMs. A TPM implements a bunch of crypto algorithms. So it supports elliptic curve crypto, it supports RSA. You can do message authentication codes, HMACs. You have a bunch of hashes, you have asymmetric ciphers. It also includes a bunch of weak ciphers, which you should not use, but it's in the specs, so they have to implement it. It has a cryptographically secure random number generator. It also includes multiple, and that's basically the core of a TPM chip. It has multiple key hierarchies. So you have like multiple ways or multiple sources where you can secure your data with. TPM, and I'm talking about TPM 2.0 here. The older TPM spec is a bit different, but with TPM 2.0, it's platform storage, endorsement, and null, which is not really used. Key hierarchies, and you also have authorization. We will get to that, platform configuration registers, PCRs. You also have a bit of persistent storage in there and a bunch of other things. But these are the main ones which are usually used. Okay, let's briefly recap or talk about what the common uses of a TPM chip are, especially on PCs or laptops. It's used for secret storage, right? So mainly disk encryption. This is what it boils down to. You have like disk encryption enabled on your system. Either it's just one partition or it's the whole disk, and then you have a key for that. The key is either derived from a password or you have it randomly generated, and you want to store that securely. And this is where the TPM comes in. You can like use the TPM to encrypt your key, and then you can store it on your normal disk. And only with the TPM you're able to decrypt it again. Yeah, you can also include a PIN, so a low entropy password in there. So when you boot up your laptop, you have to like enter the PIN, and then the TPM will allow you to decrypt the key. You can also do the same thing for TLS VPN or SSH, so you can secure those keys also with a TPM chip. Yeah, the key hierarchies here are used to actually protect the keys. So those keys itself are used to encrypt your keys. And these root keys are not able to leave the TPM. So the TPM protects them internally and it will never give them out to you. This protection is called binding. So just when I use the word binding, you know it's that. Yeah, there's also small internal storage, as I mentioned, so you can actually store your encrypted keys on the TPM, or you can derive new keys and store them in the TPM internally, but usually you want to scale and you want to have multiple keys, and then the storage internally doesn't suffice, so you can store them outside of the TPM, which is fine, because the TPM encrypts them and will give you the encrypted data blob, which you can store. And without the TPM, you cannot decrypt it. Yeah. The client will then, as I mentioned, during boot up, take the blob, give it to the TPM, which will unbind the key, basically decrypt it, and give it back to you. And I should also mention, it also verifies it, right? So it's not just encryption, it's also authentication. So the TPM will know if you've tampered with your blob and changed some bits. And the second main use of a TPM is measured boot. That's not to be confused with verified boot, which is the common marketing term for this is secure boot. Verified boot, secure boot is you verify signatures, right? With measured boot, each boot component will actually measure the next boot component into the TPM, which is basically, we'll take the binary, produce a hash, and this hash is added to or appended to a PCR register in the TPM, which will not allow one or the client, which is the PC or the CPU, to modify that register again. So you can just append data there. You cannot change the value directly, but you can append measure data into it, and it will change its value depending on the data which you give it to it. And this is used to ensure that once you've booted up everything, the TPM will have certain values in the PCR registers. And you can verify those values. So in the end, you can look, when you have booted your application, you can check if those PCR values match what you expect them to be. And then you can ensure, thereby you can ensure if the whole boot chain is the same way you've set it up to be. And also you can combine it with secret storage. You can use that PCR values in the binding process or during the encryption, so that you tell the TPM those PCR registers have to have these values for that key to be decrypted. If they don't have the value, so if somebody's, let's say, changed the kernel or changed the bootloader, the TPM will not decrypt your key. The third one, and I'm not going to talk about it in full detail, is attestation or remote attestation. Basically, you can ensure remotely even that your device is in a known secure state before you interact with it. So when a device wants to connect, you can run the whole protocol of ensuring that the device state is actually what you want it to be before you interact or let it access some secure resource. That also involves PCR registers, that involves a lot of features from the TPM, like the attestation key, and the trust chain which you verify to actually ensure that the TPM is the right one and the TPM state is okay. And as a result, you get like a signed quote from the TPM, which you can verify on the server side. If you want to know more about that, there's a great talk, not only one by Matthew Garrett, who's done a lot of work on that for Linux. But now let's really talk about TPM on embedded devices. As I said, it's not very common, but it's possible. It's actually, with embedded devices, you have about a bunch of things which are different. We've seen here before, there's BIOS or UEFI here on a standard Intel PC. With an embedded device, you don't have that usually. You have like some special boot ROM, which is specific to your system on-chip vendor, which then will load a next stage bootloader and maybe even another bootloader before your kernel actually runs. So with an embedded device, you have to somehow, if you want to use measured boot, have to somehow re-implement all of that and have to find ways to do that. Often it's ARM-based chips with embedded devices, so you don't have UEFI, as I mentioned. You need to ensure that whatever starts as UEFI or whatever comes here is verified too. On embedded devices, we usually have U-boot as a bootloader, which actually implements UEFI, so it can act as somewhat UEFI itself. So you just have to sign the U-boot and then verify the signature using vendor-specific tools. But then you can start the whole measured boot chain like you do on a regular Intel-based PC. Yeah, you can also use, you don't really need a TPM chip. You can also use like a software-based one, so FTPMs. You can run them with ARM, you have a trust zone. You can run them in the trust zone, which is like a dedicated trusted execution environment on your chip. So the OS there, which is open source variant, is Opti, emulates a TPM chip. And for the main CPU or the kernel, it looks like there's a regular TPM chip there. And you can even run the whole measured boot chain from U-boot's emulated UEFI. So you load the necessary blobs and go all the way up to your kernel. There's a great talk by Manuel Trout from All Systems Go last year, which exactly explains how he did that in full detail. When we talk about TPMs, and that's the main thing we usually talk about with our customers, you have to compare your threat models. TPMs are mainly used and understood on laptops or PCs or on your desktop hardware. And for embedded devices, the threat model is a bit different. First one is, on a PC, you as a user, so I as the owner, want to protect the data that's on there. So thankfully I'm in control, I can configure everything, and I want to secure that data which I put there. On an embedded device, it's usually the producer, so that the company which creates the device, which then gives them out to users. But it's not the user who wants to protect data on there, but it's usually the vendor of the device who wants to protect their intellectual property or some secret keys to access their backend, for example. And that makes the whole setup a bit different, because as a user, I can ensure physically that nobody gets easy access to my laptop, but as a vendor, I sell it, right? So I can go to the store, I buy one of those devices and have all the time I need with that device to tamper, to try and do everything I want with it. So the TPM is put, or the whole setup is put under much more scrutiny. You also have no physical presence on, especially IoT devices. Think of your camera. There's no physical presence. There's nobody who can input a pin once the camera boots up. Which is also an important factor, because with the TPM, I can ensure that once that thing is booted up, I have to enter my PIN or password before the TPM will even unlock or unbind the key. And on embedded devices, that's not possible usually. Embedded devices are usually run 24/7, so it's not like it's shut down, it's booted up again. And that makes a major difference with measured boot. When you go back here, as you can see, measured boot goes up into the kernel. Once the kernel is measured, measured boot is done. So everything that happens at runtime, measured boot will not care. Oops. Wasn't me. Thank you. So at runtime, measured boot does not work or is not active. Once it's measured the kernel, we know the states of the PCR values. You can, in fact, actually do stuff here and produce new measurements for the TPM chip. That works, but you have to actively do that, and you have to implement that. Yeah, you also have longer life cycles, so usually an embedded device is at least out in the market for 10 years or more. Think of your PC. It's 5 years, usually. But the upside is you have a lot more control on an embedded device. On an embedded device, you control basically everything. You control the hardware layout, you control what is run there. It's not the standard generic PC where users decide what they run on there. As a producer or as a vendor of such devices, they really decide what's running on there. So it's a bit easier to lock down and to throw away certain use cases which they don't need. Okay, let's come to really pitfalls and common threats with TPMs on embedded devices. One major thing is performance and also cold boot attacks, which go basically hand in hand in this case, because cryptography on TPMs is really slow. A TPM is not like a crypto accelerator, which can do symmetric ciphers really well or fast. It's slow. So it's good enough to do asymmetric crypto. You can give it data. It will encrypt it for you and will give it back to you, but it cannot run like your symmetric TLS cipher. So it does not run AES at full speed. Should I try turning it off and on again? Yeah, let's get a whiteboard. Nothing? Oh, there it is. Okay. Okay, as I mentioned, performance. So the main thing here is for using the TPM, you have to get your encrypted data back to the CPU. So at some point, it's in memory. So cold boot attacks are actually an attack vector with TPM protected keys, because you will have them in memory once in a time. Think of full disk encryption. You boot up your device. Initially you enter your PIN. The TPM will decrypt the key, and then your kernel will load the key into main memory, and then it will stay there because you need it when you write to the disk or read from it. So you need to add and think of dedicated measures against cold boot attacks. Otherwise, and the TPM will not do that for you. You will need to handle that extra. Then there's runtime integrity. I also mentioned already that measured boot is done once the kernel is running, usually. You can also add more and produce more PCR measurements later on, but you have to actively do that and have to consider which PCRs you want to measure into and how to check them. For disk encryption, there's one thing you can do, and which is usually also done by things like systemd. They produce a new measurement once the disk is mounted. So once the TPM has unsealed the key and the key is used for disk encryption, they produce a new measurement into one of those PCR wedges which they bind the key to. So the TPM after that will not, I didn't do anything. Okay. So the TPM will not after that produce the key or decrypt the key. This way you can at least ensure that during runtime, your key will be in memory, but somebody who gains code execution on the device cannot really get it out of the TPM directly, but has to first reset the device and maybe try to get in before those measurements are done. Yeah. You can also have a bunch of additional measures which are also common sense pretty much. You limit your privileges per process, so don't run everything as root, set proper file system permissions, get stuff like SA Linux, AppArmor running, use IMA EVM, which is really giving you in runtime integrity. And also, main thing, which sometimes vendors do forget, use unique keys per device. Do not use one key for all devices. Then there's direct physical attacks. You can, with the TPM chip, and especially with embedded devices, as I mentioned, you have all the time you need. You can open up the enclosure. You can attach pins or probes or whatever, everything you want to the TPM directly, and you can try and see if the power it uses somehow gives you a clue on the key. So all the side channel attacks are there. With the TPM, they usually have something like a bit of protection, but a lot of it is, from what I've seen, a lot of security theater. They tell you it's protected, but often it's just coating over the chip, or it's some tamper evidence, which will just show you that somebody has tampered, but it will not give you full protection against tampering. One tip is to look at the FIPS 140-2 or -3 certification of the chip itself, because that level which the vendor gives you will tell you how good the chip actually is in doing physical protection. But there are actually easier ways to tamper with the TPM chip, and that is looking or listening on the bus, which sits between or which connects the TPM to the CPU. And there's actually a bunch of research being done there, and that there have been a bunch of attacks. I mean, Windows PC are known to, I think every 2 years we get some new BitLocker decryption variant for how to get the key out of the TPM or listen on the bus and extract the key. It's a lot more easier than it sounds. They're really hardware you can just buy for a bunch of euros and use that. And then listen on the bus lines, what the TPM and the CPU are actually exchanging. Because oftentimes vendors do forget to encrypt that. The TPM offers features. There's something that's called HMAC, session-based commands or response parameter encryption, which both of those things you want to use to ensure that once the TPM decrypts something, it will not send it in plain text over the bus. There are multiple modes which you can configure, but the client, as I said, needs to enable those specifically. When you use, I think, systemd and the mcrypt, so the systemd, Lux2, and the mcrypt integration does that for you. But not all other clients. So if you have a custom application, usually you have to take care of that yourself. Then there's active interposer attacks. The previous one, we were just listening on a bus. Now we're trying to also talk on the bus and be faster than the TPM and launch a man-in-the-middle attack between the TPM and the CPU and have the CPU talk through us to the TPM. For that, again, you have like encrypted, authenticated sessions, which are when used properly, are good and help, but they're not perfect. Systemd already tries to do something like that. It places a metadata or a hash of this storage root key, which is one of the keys inside the TPM, on the disk, and uses that to verify if the TPM it's talking to is actually the TPM which it set up. That works, but it also has a bunch of caveats and a bunch of things you have to take care of. I think it's solved now. There's a GitHub issue where they talk about in length about that, but I think they ironed out most of the issues right now. Yeah, the problem is still an interposer can reset the TPM. So once the TPM is reset, all the PCR values are reset, which means, again, measured boot can be bypassed, and you can, after you've reset the TPM, you can produce new measurements to the TPM, and if you know what you need to measure into the TPM, those measurements can reflect what you need it to. So in the end, if you have an issue, you produce an update, you can reflect, if you reset the TPM, you can reflect an old state in the TPM and maybe decrypt an old key, which likely did not change during the update. The Linux kernel is one of the parts which needs support for that or which helps you in that. It recently, with 6.10, gained the ability to partially detect this. What the hell is going on? But it still requires user space to do full attestation of TPM's EK certificate, which is again a certificate in the TPM or a key in the TPM, and there's a certificate which you can verify. If you want to know more, there's a great talk by James Bottomley, who does all or many of the kernel side TPM stuff, and this year he talked at FOSDEM about that. Yeah. There's TPM and firmware flaws. I mean, TPM runs software. Those firmware stuff can have issues as well. This has happened before. There's the famous TPM fail CVE from 2019. Sometimes you can fix that by update, but sometimes you don't. So if you have an old chip and consider lifetime, you have an old TPM chip there, which might be still used in, they say, 10 years, and it has one of those issues. It will have that until the end of its life. Yeah. There's also been another vulnerability, this so-called ROCA vulnerability, where they really have hardware vulnerability itself inside the chip. What you can do there is not much really, but you can try to do additional hardening of the whole system and backend. And as I mentioned, unique keys might be a good idea then. Yeah, then there's software-based issues. If you use a software-based TPM, it's nice actually because it's a bit better than a physical TPM because it prevents the whole listening on a bus thing because there's no bus. It's basically the same chip. It has a dedicated execution environment, but those things can also be vulnerable. There have been trust zone flaws. There have been there's the fault TPM vulnerability for I think AMD CPUs, which has been pretty famously gone through media some time ago. So they're still vulnerable to some kinds of attacks, like side channel timing leaks and so on. When you do it on an embedded device, you might run Opti there. You also have then to take care of, I mean, Opti is running your TPM, so the TPM is responsible for securing keys. So you have to somehow store the keys again, which the TPM internally holds. There's solutions there. Opti uses something that's called, with an eMMC, you can use the RPMB feature, which is a dedicated hardware feature from an eMMC, where you can store the keys. But again, that needs a key. So it's a chicken and egg problem. Yeah. And let's come to an end here. There are alternatives to TPMs. I mentioned a few. There are often vendor-specific solutions. I mean, a bunch of industrial embedded devices use system-on-chips from NXP. They have really their own products, which they sell you with the chip itself, which offer similar features, but maybe even better ones because they sit on the same chip, and so there's no bus. But you need support for that in the kernel side. Yeah, there's, as I said, custom-based solutions which you can work on with ARM Trust Zone. You do not have to use Opti itself. And you can also use dedicated hardware. I mean, Apple is doing their own thing with secure enclaves. They really did not use only a dedicated chip, but that chip is actually holding everything internally, and even they pipe through a lot of hardware connections through that chip, so they can authenticate everything. Okay. Let's come to really an end here. TPMs are definitely an option for embedded devices. They are not that common, but we can reuse a bunch of features from PCs, like disk encryption, as I mentioned multiple times. Systemd really integrates with TPMs already, so you can use that on an embedded device as well. But the threat model is slightly different, and in some areas a lot more different. So the TPM alone will never solve everything for you. You have to do additional things, and you have to know them and take care of them yourself. Yeah, Thank you. That's it. And sorry about the issues.